In March of 1979, a scientist named Stan Peale published a paper in the journal Science that made a claim many of his peers found ridiculous. He argued that Jupiter's moon Io, a small, freezing rock the size of our own moon, was actually covered in active volcanoes. Peale had no direct evidence. He didn't have a single close-up photo of the moon, nor any telescopes powerful enough to see the surface. He was relying entirely on the mathematics of gravity, and if those calculations were even slightly off, the error would likely end his career. The deadline for proof was immediate. The Voyager 1 spacecraft was scheduled to fly past Jupiter and its moons in exactly 3 days, and its cameras were about to provide the first clear look at Io's surface. Voyager passed the moon and sent back thousands of images, but they didn't show what Peale expected. Scientists saw a colorful, mottled surface, but no eruptions, no lava flows, and no ash plumes. For a full week, the visual evidence seemed to confirm that Peale was wrong. This moment highlights the danger of theoretical science. Peale had bet his reputation on a mathematical model that the physical world, at least initially, seemed to ignore. 4 days after the flyby, Linda Morabito, a 25-year-old navigation engineer, was processing a series of routine alignment photos. These weren't the science photos being analyzed for discoveries. They were low-quality navigation shots meant only to verify the spacecraft's position. While adjusting the brightness to see background stars, she spotted a faint crescent-shaped cloud hanging off the edge of the moon. It was massive, reaching 270 kilometers into the vacuum of space, a feature that shouldn't have been there. After ruling out camera artifacts and background moons, Morabito realized she was looking at a volcanic plume. She had found the evidence everyone else missed, proving that Peale's mathematical prediction was correct. This observation ended the long-held belief that Earth was the only volcanically active world in the solar system. Suddenly, the count had doubled. But the discovery created a new mystery. Io sits in a frozen region of space where temperatures drop to negative 130 degrees Celsius. How does a small, ice-cold moon generate enough internal energy to blast sulfur plumes nearly 300 kilometers into the void? The moon is heated by a gravitational engine called tidal flexing. Io is trapped in a gravitational tug-of-war between Jupiter and 3 other Galilean moons. Because its orbit is an oval, this pull changes constantly. Every 36 hours, the moon's solid surface is stretched and squeezed by 100 meters. This relentless motion creates massive internal friction. The rock itself generates heat as it grinds together, creating a reservoir of energy that melts the moon's interior from the inside out. This leads to features like Loki Patera, a lava lake over 200 kilometers wide. Every 475 days, the heavy, solid upper crust cracks and sinks, completely replaced by a fresh layer of glowing lava from below. Io's mountains are equally strange. They don't form in ranges. They are solitary, 18-kilometer-high pillars that burst straight out of the ground. This happens as the surrounding surface sinking under the weight of new volcanic deposits, forcing adjacent blocks of crust to violently thrust upward. This constant gravitational strain has turned Io into the most hyperactive environment in the solar system, a world that is continuously resurfacing itself through violence. For decades, the standard explanation for this activity was a global magma ocean. Scientists assumed that beneath Io's crust lay a continuous layer of liquid rock that allowed the surface to flex so easily. In 2024, NASA's Juno spacecraft performed close flybys to test this. By measuring exactly how much Io's shape distorted during its orbit, Juno could finally confirm if that global ocean existed. The data was unexpected. Io was far more rigid than a world with a subsurface ocean should be. It wasn't deforming like a flexible water balloon. It was resisting the pull like a solid object. This means the magma isn't one big ocean. Instead, it's trapped in hundreds of isolated, independent pockets. Each volcano on the surface is fed by its own local reservoir, acting as a separate volcanic engine with its own unique cycle. Juno's measurements replaced a 45-year-old consensus with a new reality.
Io's heat is managed by hundreds of independent reservoirs rather than a single underground ocean. This volcanic violence is actually a slow form of self-destruction.
Every time a plume erupts, it blasts sulfur and gas permanently into space. Io is literally throwing its mass away, losing material that it can never recover. Meanwhile, Io's orbit is slowly becoming more circular. This means the intense gravitational tug-of-war that generates its internal heat is gradually losing its strength. Eventually, the friction will stop. The isolated magma pockets will freeze solid, the mountains will stop rising, and all 400 volcanoes will go silent. If we were looking at Io a billion years in the future, we would see a dead, cratered rock. We only know about its incredible geology because we happen to be watching during its most active phase. We are lucky to witness Io in its prime. It is a reminder that our understanding of the universe is only as permanent as our latest observation, and a single flyby can reveal a reality far more intricate than the one we had previously accepted.